My name is Eric. I'm working at EPFL, the Lab for Creative Computation.
I'm Dalila, same as him. And today we're going to present reconfiguring with COMPAS. Circular strategies exist along a range: salvation after demolition, design for disassembly, component reuse. But the most resource-efficient approach: never fully take the structure apart, reconfigure it in place. And that's what this project is about. Not demolition and reuse, but in situ reconfiguration. There are timber structures like this worldwide, and the question is, how do we use technology to reconfigure them? How do we go from point A, the old structure, to point B, the new structure, and the virtual model? We will show you how we did this. Existing hand-built structures carry uncertainties digital models don't represent. Dimensional variations, hidden joints, and structural dependencies that only emerge as you operate. Conventional robotic workflows don't handle this. They assume everything is known before fabrication begins. And also on our structure, what's built never fully matches the model. What we need is flexibility built into the process, and that's where COMPAS comes in. The human is not an operator. They are an active designer throughout. The robot handles heavy, precise work, but what no sensor can replicate is constant qualitative judgment. Is this joint sound? Can this wrap member still serve? Every placement involves moment-to-moment decisions that are too fine for any model to anticipate, like rotating a member for a better face or burying a defect inside a connection. But they continuously shape the outcome. Neither can do this alone. The framework supports both. And how does design actually work? You start by sketching a global direction. Some elements are marked for removal without a destination yet, and then you roughly arrange the rest into the model to establish new spatial conditions. It doesn't need to be precise, and dimensions don't need to match the available stock perfectly. It's just an approximate target and not a resolved design.
Right, so we're really working from this idea that we have a design direction and not necessarily a fixed plan. As Dalila was saying, the material is really full of unknowns, which is par for the course with this idea of working with reclaimed wood. So rather than trying to fully characterize everything before we start, we took this approach of kind of building into the process this idea of an adaptive approach. And so from the beginning, the question was what kind of tech stack we could build around if we're working with this idea with robots in a nonlinear way, and also expecting that the material and the structure itself in the end would deviate from its digital form. So COMPAS clearly played a major part, which is why we're here. Before we get into some of the more technical aspects, this is kind of the baseline hardware that we're working with. So two 6700 IREs on parallel tracks, 3 tools, 2 grippers in total, 1 for each robot, a chainsaw which we were able to swap in, as well as 2 3D cameras mounted on each robot. And so across the robots, sharing a workspace, and then also our need to oftentimes control them in tandem, as well as utilizing maybe some more unconventional tools. All of this wasn't really a problem when we were using COMPAS. So now we're getting a bit more into the workflow. It's really built from this idea of a parameterized element-based approach. So each timber member within the model is a discrete object we're able to select and then assign operations to. Everything kind of flows from that. So what we'll get into with the planning and the scanning all kind of stems from there. Geometry-wise, every member is abstracted as simple rectilinear geometries. So this is a kind of intentionally rough approximation that we took because we knew there were bound to be gaps between this digital model and the reality, but this is why we kind of built in this idea of localized scanning. So what matters is that it's really close enough for us to sketch with, and then we can really get real geometric understanding piece by piece. In addition, this approach allowed us to do some more useful kind of upfront and rapid computational steps, which rely on model abstractions. So for instance, we have a Caramba 3D integration, which allows us to run in parallel this structural decision-making support. So it'll update live as we change the structure, but then also You can see at a glance which members, for instance, we could remove, or generally just inform the next steps we could take. From there, we get into more of the parameterized action model. So each action type has its own logic built in, but they all target different frames. The COMPAS fab, we can use COMPAS fab to plan around. So for instance, here is just a distinction between cutting and moving. Moving kind of encompassing a bit of everything where, that includes replacements, removals, things like that. But regardless of what the operation is, in the end, we generate a set of scan poses, which we can kind of plan around and then also tweak. This is a bit of how each action is constructed. So for a cut, you pick a length along the member and face, and it kind of generates then the start and end planes. For move, similarly, you can define a place on the member to grab, and the planner generates collision-free paths from there. Crucially, what's worth mentioning here is that both robots are in the planning scene simultaneously. So for a cut, one member grips the member for stabilization while the other approaches. From there, we move to the scanning phase. So once the robot reaches the poses that we define initially, then we call the Zivit SDK to run the scans. Typically, we have more than one scan. So from there, we can merge point clouds to create a more complete picture of the real geometry of the structure. From there, we can determine what the real surface is that we're working with. And then we can also update the collision objects in the COMPAS fab planning scene so that we really work against the real structure. You can see that here where the workflow kind of loops back so we can continuously scan. That's used to correct the pose, finding the real surface in Grasshopper, and then from there we plan the path. This is a bit of a breakdown of the process. Before we choose an element that generates some planes that we can work with, but we want to actually modify these based on the scan planes that we have. So once those are merged, we can do the correction. And yeah, last step, we send instructions via COMPAS RRC to the robot. And this is where the human operator can confirm on the teach pendant. Our focus here has been mostly on the robot side, but it's worth mentioning that as Dalila was talking about, the human role is just as important for us in this idea of a collaborative human-robot process. So for the human, we think about as doing finishing steps, but we can also have them in really part of the process to make qualitative calls. And really from the beginning, the workflow was supporting this kind of idea of a back and forth rather than assuming everything to be automated. This is a bit of a moment that we recorded early on where we encountered maybe our first discrepancy. So, video showing, yeah. And it just kind of demonstrates this idea that, in the real structure doesn't always match up to what you have digitally. So I think you saw that it was kind of colliding with this vertical member, which we didn't anticipate. And so that was one of our learnings where there are these kinds of things that happen with existing structures, and exactly why we design the workflows the way that we do. Very, very quickly, this is a side-by-side of kind of what we had in mind at the beginning of kind of how we phased out the design and then how things really happened. It's worth mentioning that while we didn't pre-plan everything, we kind of decide to have some organizational phases, so things like doing the roof first or the envelope first. And in the end, the deviations weren't so drastic, but we did have some changes in the design that then had knock-on effects. For instance, if we made a column earlier, that would affect kind of the reachability and the collisions for future moves, which we were able to work around flexibly.
So the framework was validated by reconfiguring the initial structure into a two-level microhouse for human occupancy. And out of the 63 original members, only 3 got discarded and only 2 new elements were introduced. 2 columns that needed to be longer than what we had in our existing stock. And this is the end structure, referencing the initial one that had a sloped roof and introducing 2 platforms, which help us to create different spaces to make it more livable. So the target geometry adapted to the material we had and not the other way around. Yep. Thank you for your attention. And if you want to learn more, scan the QR code.
Thank you very much.